I'm talking about this self-evolving and transformative communication for ubiquitous intelligence. And we know that ubiquitous intelligence requires many real-time interactions among human, cyber system, and physical systems. And these ubiquitous intelligence applications, many of them have much stringent quality of service requirements compared to the traditional internet applications, such as AR, VR, hologram, distributed systems. Learning, they require very high data rate. And the V2X industry control systems, robotic UAV swarms requires extremely high reliability and very stringent on-time and in-time services. From this figure, we can see the time requirement is very stringent, like a few milliseconds or even below 1 millisecond. However, our internet TCP/IP network was originally designed particularly for human consumers. Humans are the ones to consume information. Humans are intelligent, weak, and resilient to delay, loss, error, while in cyber-physical human interaction situations, when the information needed to be received by algorithm machines, they have much more stringent and high-dimensional, multi-dimensional quality of service requirements. And on the other hand, for ubiquitous intelligence, we can imagine like the communication system needed to cover much more than today's internet. Not only where the internet exists needed to be covered, but also those rural, remote island, depopulated zones needed to be covered, even above underwater, like ship AUVs. Or we can see like in space and air, we also need the coverage through UAV, drone, balloon, or all kinds of satellites. And with this ubiquitous coverage, we noticed that we needed to have heterogeneous wireless communication links to support this ubiquitous coverage, spectrum-wise from sonar microwave to terahertz laser. And these different wireless links has quite a diverse physical medium and communication technologies. And these different link characteristics demonstrate different constraints, such as like underwater or satellite communication system has extremely long propagation delay, very limited spectrum, limited energy, and limited coverage. And some other systems are quite sensitive to weather. So we also noticed that we even need to handle different types and the levels of mobility when we have UAV, AUV, and satellite to be part of our access or backbone network. So to support ubiquitous intelligence, we not only needed to support traditional user mobility, but also need to support network mobility and how our communication system to adapt to these different types of network and mobility patterns is a great challenge. And we also noticed that for human and physical cyber systems to exchange information, in many cases, we no longer have the situation of unicast, which means the information is sent from one user to one receiver. We very often need to deliver information from one sender to multiple receivers through broadcast, multicast, or from multiple sender to one receiver through incast, or from multiple sender to multiple receivers simultaneously, which is called a groupcast. And we know our internet TCP/IP protocol stack was designed mainly for unicast. And we encounter a great challenge to support all kinds of multicast, broadcast, incast, groupcast. Here we use starcast to represent that. So how can we leverage the broadcast medium feature of wireless communications to support this starcast application for ubiquitous intelligence is a big issue. And finally, for ubiquitous intelligence, we not only need to deliver data from sender to receiver, but also we want to generate information and share knowledge among intelligent agents. So future communication systems to support ubiquitous intelligence, we need to integrate sensing, computing, control, and communication together. Specifically, these communication system needed to integrate with sensing signal processing capability to collect data, using caching content distribution to store data, and using different types of coding and compression to process data, as well as apply various AI technology, machine learning technology for network management and control. And in addition to that, we also want to have our system support various types of centralized and distributed learning and AI applications. And we know that our traditional internet TCP/IP was designed for data pipeline only, not suitable for this kind of integrated sensing, computing, control, and communication. So if we take a look of the internet architecture, internet has this kind of hourglass architecture. In the middle is TCP/IP protocol. In the top, we have various types of applications on top of various types of communication links. And we notice there are many issues with this internet architecture, such as for TCP/IP, they cannot provide end-to-end service guarantee. So TCP can provide certain types of reliability, but cannot guarantee other things like delay, jitter, throughput. And in this layered architecture, we also notice that link layer and end-to-end transport layer has many redundancy. And sometimes, for instance, link layer retransmission and end-to-end layer, end-to-end TCP layer reliability control, they will conflict with each other, results in reduced efficiency. And in today's wireless system, we often use tunnel over tunnel to solve the problem. But this kind of tunnel over tunnel introduce a high complexity and overhead not suitable for ultra reliable low latency service or massive machine type of communication, which is critical for ubiquitous intelligence. So if we take a look for our wireless system from 1G to 5G, currently the most state-of-the-art 5G system takes this cup architecture. Cup means user plane and control plane and user plane separation. So this cup architecture will separate the control plane and the data plane, although signaling traffic like user authentication, registration, mobility tracking, they will go through this control plane using the protocol of SCTP over IP, while the user's data, multimedia data, voice, video, text traffic, they will go through this user plane to mobile call using the protocol like GTP over UDP over IP. And this kind of cups architecture has the nice feature that we can push all this control function into cloud using software. And this will give a little bit much more flexibility to deploy these control functions and make the system more efficient. However, we found that given the existing both internet and 5G architecture, there are still something missing, particularly when we needed to support ubiquitous intelligence. We found its lack of fast control in the granularity of less than second or millisecond level. So we noticed that because of the propagation delay is unavoidable. If we push all the control function into the cloud, the propagation delay will take tens or hundreds of milliseconds. So this is too slow to make any decision through such long distance. So we notice that this kind of fast control must be in the flow packet level, needed to be rely on our communication protocols instead. Okay, so this is our design objective. we want to propose a new protocol architecture which has this feature. With this new protocol architecture, we can assemble a protocol to take a wider range of control function, this protocol itself can self-evolve and transform for different applications with different quality of service requirements. And it can support all kinds of Starcast service modes. And it can be adaptive to very dynamic environment in a ubiquitous coverage, space, air, ground, water coverage. And eventually, this new protocol will be able to support ubiquitous intelligence. And the first step we want to do is, based on today's separating of data plane and the control plane, we found that in the control plane, we needed to do certain further steps. Basically, we want to divide the control plane into different layers based on the control time scale. So for instance, the right-hand side is the user control, such as user-associated billing accounting. So those kind of control function can tolerate a second or several second delay. So we can push it to the cloud. And in the middle is session level control, like session level authentication policy rules, mobility management. So this is still can tolerate hundreds or more milliseconds. So we can put it either in cloud or edge server. And the left-hand side is flow packet level control. So these types of control needed to be very fast in millisecond level or even sub-millisecond level. So these must be associated with the data plane. So in the data plane, we need to add this control unit we call the in-network protocol control agent. So this control unit will be used to deal with anything packet or flow level control with very, very low latency requirement. Okay. So with our cubic model, like control plane is separated to different layers, and in the data plane, the data plane will be associated with this flow packet level control. So with this qubit model, our network architecture will look like this. So this user control and session control could be put in the cloud, in the central server, and then in the data plane and the flow packet level control. These need to be deployed along our network end to end. So every network device needs to support both data plane as well as flow packet level control. And this flow packet level control is handled by, we call the protocol control agent. Okay. So now we are ready to develop this new architecture. The protocol follows this new architecture we call the self-evolving and transformative intelligent protocol architecture. So to achieve that, we first of all take a look of the traditional protocol architecture. So we found that in today's internet, either we use a one-fit-all approach, like we develop IP protocol to support all applications without much concern on what types of applications running on top of it. Or we have this one-for-one approach, like in the application layer, we develop new protocol for new applications, and we cannot reuse existing applications. Okay, so our new protocol architecture, self-evolving and transformative one, we hope it can be able to serve a large number of applications and consider their needs. So how to achieve that? We can learn from other domains like object-oriented software or operating system. The main idea is to take the modularity. So in the protocol design part, we can also take this modularity approach, which means we can decompose protocol control functions. So a protocol can be assembled and configured using different control blocks, control algorithm, or configurations. We can use an example, for instance, in the transport layer, TCP. Right now, it provides one service. This is connection-oriented service with reliability, error control, and with flow and congestion control. Okay, but if we decouple all these functions, we found each function can be divided into certain procedure And for this procedure, we can use different types of control mechanism to handle that. For instance, for connection management, we can either use handshake-based or timer-based, so on and so forth. So once we decompose these control blocks, we found that like each function, we can have multiple choices. In this example, we have 3 choices, 2 choices here, or we turn off this block, so 3 choices. So by combining these 3 choices for each function, we can have 3 to the power of 4, 81 different combination of these control blocks, which means we can reconstruct this protocol to provide 81 different types of services. Right? So we can see with this modularity approach, by decompose and reassemble, each protocol could be much more adaptive than today's internet protocol. Okay, so given the time, I probably want to go much detail. And the key issue is we need to have this protocol control agent which can assemble this protocol. Like each protocol has already been break down into blocks, and we can use all kind of machine learning AI technology to decide, given the service requirement, given the measurement in different layers, how do I configure each protocol using the right control blocks, and how to set their parameters accordingly. Okay. So this protocol configuration and adaptation is the key part. To make it simple, we can begin with some like menu or default configuration for easy start. And then based on the real-time feedback from the network, the real-time requirement from the application, we can keep on changing. So essentially, this is a sequential decision problem. For this sequential decision problem, which is the protocol reconfiguration part, we can apply many advanced machine learning reinforcement learning tools like MAB or LLM to solve that. Okay, so quickly summarize. So here we try to promote a new architecture for ubiquitous intelligence. So this new architecture, different from today's approach, we highlight in-network intelligence. We want to put protocol control agent in each network entity, and this PCA can take information from different places, and they can also coordinate with each other to achieve end-to-end quality of service support. And because of we put the intelligence in network, so this distributed intelligence can react to network dynamics, channel dynamics, and application requirements much faster, robust, and efficiently. And because we can always reconfigure the protocol, so this protocol has a self-evolving and transformative feature, which can be used to support Starcast service modes. And in our team, we have applied this new architecture idea to develop new packet level service guarantee protocols to better handle mobility prediction and management, support a better Starcast service, try to integrate sensing, computing, so on and so forth. Okay, and I think given the time, this concludes my talk. So we try to come up with a new protocol architecture to better support service requirement for ubiquitous intelligence, which has the feature of distributed coordination, user-centric spectrum mobility management, and it can support adaptive Starcast mode. Yeah, there are many open issues for future research, such that how to decompose the whole protocol stack and build new control function, how this control agent PCA effectively discover network environment, how frequently to explore map the QoS requirements to control policies, and the distributed intelligent agents can also leverage advanced AI machine learning to enhance network security and data privacy. So all these are leave for future exploration. With that, I conclude my talk.